back. So we have the second lecture by Samir Mathur on the quantum nature of black holes.
Okay, so let's start by recalling what is the problem we were looking at last time. So I copied one slide back from what you saw yesterday. And so this was the problem. If you make a black hole, all the mass goes towards r equal to 0. That's like a point. Let us draw it like a point. And then there's this whole region we call the horizon around it. This space is all empty because everything went to the center. But then around the horizon, the vacuum is actually unstable. And it's unstable because the particle put in here, its net energy can be negative because of the gravitational potential is so negative. And so if you have both negative energies inside, positive energies outside possible, then there are zero energy states you can make, which actually have not the vacuum, but a pair of particles. So that's how a state becomes unstable. When there are other states of the same energy, like the vacuum has no particles, maybe energy 0, and if I make a pair of particles, but if the energy of one is -1, one is +1, total energy 0, it has the same energy. And then you can just move from this to this, and if there are many such states, like 2 pairs, 3 pairs, they all have energy the same. So you can, the state will just keep drifting and keep making these pairs. And that's basically what we saw with Hawking's discovery. The outside particle goes out and becomes Hawking radiation, and because this guy has negative energy, it reduces the mass of the black hole, so that way energy is nicely conserved. The problem, of course, is that as this thing gets near the end point of evaporation, we saw there was a problem. Because now these guys were heavily entangled with these guys. If this is an electron, then this is a positron, this is a positron, this is an electron, and because the state is a superposition, these guys don't have a state by themselves. This guy and this guy together have a state. And that is fine up to here. You can always have entangled states. But if the mass of this has gone to 0, you might think maybe it will just vanish. But if it does that, then of course this guy doesn't have any state at all. And that's the kind of problem where we were last time. So you can see all this trouble is happening really because gravity has an attractive potential. And because of the attractive potential, you can have a lot of structure, a lot of particles. But if they are sufficiently close, then all the rest energy mc squared can be cancelled by the minus g mm over r, and you can again come down to something with no mass. So just once you have negative potentials, you can keep making versions of this problem, and the question is how do you get out of it? So at this stage itself, you should have asked me a question, or you should at least might have wondered about the following. And it's something that you could ask like this. Suppose you all these negative energy particles which fell in are like the way I drawn in the picture. So when I was drawing these new pairs, I was assuming there was a vacuum around the horizon. In a vacuum, you get the pair. But suppose the negative energy particles are collecting, then of course the space seems to be getting a little bit choked up. Right? You can see it in the picture. It seems to be getting choked up. And if this guy is not a vacuum anymore, but it's already choked up with some particles, then somebody could say after some time, maybe the structure then is different. Maybe it looks more like a solid ball or something, and now the process will not happen. So then the Hawking operation will stop, and then maybe it stops just maybe halfway or something, and then there is no problem. We were saying if this process goes all the way till the guy becomes a plank, then that's when the real problem is. So these were just cartoons, and today we want to understand the problem a little more deeply. We'll see this is not how the guy actually looks. The guy doesn't actually get choked up with the negative energy partners. You actually got to see where those negative energy partners go, and that is the crucial geometric structure of the black hole. So yesterday we had no general relativity on the board, but now we slowly want to understand the black hole better. And in some sense, the goal of everything we are doing today, and maybe also tomorrow, is that at the end you should understand the puzzle so completely that if anybody comes with you saying, look, I have a solution, you know exactly what to ask him to decide whether he's talking sense or he's talking nonsense. Okay? So we really want to understand the structure of this, because right now at this level, people can give you lots of solutions. I think this will happen, I think that will happen. But soon when we understand the whole structure of the black hole, you can ask, well, how can that happen? Okay, so let's begin with the structure of the black hole. And the black hole is described with a Schwarzschild metric. So I wrote the metric here. I hope this is familiar to everyone. So you can see the funny thing about this metric, of course, is that this describes the black hole part outside the horizon. Because if you look outside the horizon, there all these are well-defined numbers, but the horizon is r equals 2m. I now put the Newton constant g equal to 1. And so at r equals 2m, you can see both these coefficients become singular, and the coordinates actually break down. So far outside the horizon, of course, this is a good metric. At the horizon, r equals to m. This is not, these coordinates break down. But as you probably know, the space-time doesn't break down. It's just the coordinates which are bad. And you can look at other coordinates like Finkelstein or Kruskal coordinates, which will take you inside the black hole also. And we'll shortly do that. Okay. But now the crucial point which you see about this metric is how do you actually make a space-like slice? Why do I want a space-like slice? Because the way we set up quantum theory, I give you a wave function on some space-like slice. And then if I give you that wave function, I've given you everything. And after that, the Schrodinger equation will tell me what is the state on some later space-like slice. Okay, so space-like slices are very important thing in life because one space-like slice through the entire universe holds all the data, and after that, it is just supposed to be evolution. But now you can see, with a black hole, the space-like slices are going to be rather interesting. And that is the entire crucial part of the black hole. Everything we have said before about negative energies being inside, those were just crude words, because of course minus gmm over r is a Newtonian potential. That was very crude. Now we start seeing what we really mean by getting negative energy inside. So as you can see, these coordinates work for r bigger than 2m. You can actually also use these coordinates for r less than 2m. It's just to describe the Schwarzschild metric. Only r equal to 2m, they're sort of disconnected because there's a breakdown. But you can see if r is less than 2m, the metric can be written, so inside the metric can also be written using these coordinates. But now you can see the coefficient of dt square will be a positive number and the coefficient of dr square will actually be a negative number. So what is the space-like slice outside the horizon? Outside the horizon, if I take for r greater than 2m, if I take t equal to constant, then you can see if t is constant, dt is 0, the metric has all three numbers positive, and that's a space-like slice. All directions are space-like. Inside the horizon r less than 2m, how do I make a space-like surface? Now this has a negative sign, so I should put r equal to constant, and then this guy, and this guy, they have positive coefficients, and so a space-like slice is actually r equal to constant. So do you see how funny that is? Is t equal to constant outside the horizon, but is r equal to constant inside the horizon? So let me just try to draw it like a cartoon. Here is my r direction, okay? And this, I don't want to call it t because t coordinate actually breaks down in this metric, but there's something called Eddington-Finkelstein coordinates. If you don't know them, that's fine. I'm not going to use any of it here. You can use Eddington-Finkelstein coordinates where the picture really looks like this. You can keep r as one coordinate and the other coordinate is something called q. It doesn't matter, just some kind of time for the coordinate. Well then, outside r equals, this is the horizon r equals to m, and far away we said t equal to constant is a good space-like surface, and inside the horizon r equal to constant, any value of r I can choose, well that is the space-like surface. Is this making sense to everybody? Okay, so what's a complete space-like surface covering both the outside horizon and inside? So it looks like something. And now everything to do with the black hole really comes from this business, because now you can start seeing several interesting things. Firstly, how much space is there inside the horizon? Yes.
Sorry, in this picture, it looks like for a given t, there's a particular r which gives the continuous space-like slice. Presumably, that's not quite the case.
No, I didn't actually mean to do that. I have to keep t equal to constant here, and then I can bring it here, I can bring it here, I can bring it down anywhere I want. Right? So in general relativity, of course, you can draw your space-like surfaces anyway. I can go up and down the many-fingered time according to Wheeler. And so I did just choose a particular place for the picture. But you can see if I choose a particular place, if I go to a later slice, the later slice should be ahead of this everywhere, it shouldn't intersect this. So later slice would be up in time and actually going inwards in r. So I can do that. Because I don't want to go too close to r equal to 0 because then the curvature is actually divergent. I don't want to get a curvature singularity anywhere because then I wouldn't know what the physics is. So then I can choose my slices anywhere I like. I will advance them here in a regular way, the way we normally advance time. But when I bring them in, I'll maybe try to not advance them too much and maybe accumulate them down to some position, maybe at r equal to m, which is halfway. It's my choice. Obviously, I can choose anything. This is just one particular slicing which you could have done for space-time. The slices are completely smooth. But look at the beauty of this. This side can keep expanding, going up, and this side just stays. I'm not going to evolve this side very much at all. So let's see if we could have done that even in Minkowski space, because in Minkowski space also, I could have either drawn my slices like this, which a normal person would do. But if you like, You could do this. You could evolve one slice more on the right, less on the left. So can you do that? You can do that, right? You can advance more on one side. So here the normal derivative might be 1 meter, and here it could be just 1 millimeter. Yes?
I guess the question is, are you guaranteed continuity across the horizon all the time?
Are you guaranteed what?
Continuity of your slices across the
Yes.
horizon.
So that is not obvious from what I drew here, but the answer is yes. You can. So in fact, in actual expression for these, in terms of function of t versus r, you can find in the notes which I mentioned. But the interesting, there's one difference between the black hole and Minkowski space. This is just Minkowski space. You can see that if I choose to not advance this side much, I want to accumulate this like I don't really want to go up here. If I keep advancing this other side, do you see if I'm going to get into a problem somewhere? Can somebody spot a problem? If one side goes up and the other side doesn't, at some point the slope here will become 45 degrees. And then the slice is not space-like anymore. Right? Space-like slice everywhere. So if I advance like a line here, this side goes up and this side doesn't go up. You can see at this place it has actually become time-like. Now in the black hole that's not true. In the black hole I can keep making this side go up and up and up, and these guys can all come down to just r equals, I can maybe, if they want, I can just join them all to r equals m, and it's a completely smooth slice. So now you can begin to see what's the funny thing which is happening about the black hole. One side goes up and the other side doesn't have to move, and this is all because the black hole geometry is not the geometry of Minkowski space. And so what you're seeing here is that if you do a slicing of the black hole by these slices, all the different slices, they actually cannot have the same geometry. See, if this slice was like this, the next slice, the intrinsic geometry of the slice is actually different. So what happens is one might think that the Schwarzschild geometry was time independent. Like this looks time independent, but that's a fake. It's a fake because it doesn't cover both the outside and the inside. In any coordinates where you try to cover both the outside and the inside, of course coordinates are only labels and they don't really matter for anything. But the physical picture, the physical point is, there is no way to draw a slicing all the way covering the outside and the inside, such that all the slices in the foliation are intrinsically, the intrinsic geometry is identical to the previous slice. So in Minkowski space, of course, there's a slicing where the intrinsic geometry is the same for every slice. You can of course do this, but you don't have to, right? But here, you have no choice. There is no way to make a slicing of both the outside and inside where the metric is actually the same, or the intrinsic geometry is the same for each slice. So the black hole geometry is genuinely time dependent. So what's the consequence of this? The consequence of this is something you learn even without black holes. It's called just the theory of quantum fields on curved space. So in just the theory of quantum fields on curved space, if you take some kind of a space-like slice, you might have a vacuum state on it. So I'll just draw that and say this is a vacuum state on this. And vacuum basically is some kind of bubbling of particles and antiparticles. So let me just draw it schematically like this. This is the vacuum state, let's say in this room. Now suppose I go and I deform this slice. So some star collapses or some two galaxies move around, no black hole yet. And the metric of this slice changes. What happens then? Well, on this slice there will be some vacuum of its own, right? Locally there will be some fluctuations which are the lowest energy state of this vacuum. But the fluctuations I had here won't in general be the fluctuations which give me the vacuum here. And whatever is the difference, that I should draw as real particles. Maybe if I have a different color, maybe I'll just draw the extra fluctuations coming off as real particles. And that's the reason why in any time-dependent geometry, you always get some pairs of particles being created. This is a very rough cartoon picture, but are you guys all familiar with the fact in curved space you typically create particles? Right? And so this is the reason, because there is a vacuum on any one geometry. If I disturb the geometry, very generically, unless you do something very, very special, the new vacuum won't be the same. This vacuum won't go to that vacuum. If it doesn't go to that vacuum, well, every state is vacuum plus some particles, so you will get some particles. It's very generic, almost anything you do, this is what you're going to get. But normally when you take, suppose you take a black hole of, not black hole, just a star. Take a star of radius, let's say, 10m, and it collapses down to a radius of, let's say, 6m. I'm trying to not go anywhere near 2m, right? So not into the black hole. And then suppose it stabilizes. Okay, it was a big star and it burnt off and came to some other size, became a neutron star. The metric changes, right? So the space-time was this, and now maybe the metric becomes this. You see, the space-time might look like this with a little dip. Now maybe there's a big dip because the metric changed a bit. And a few particles will be produced. Yeah, well, there's everything is order m anyway, so it's the same scale. So I'm just drawing it very schematic. Yeah.
But would the concept of particles be very well defined in this case?
So not really. Okay. The particle not be really well defined here, except any particle produced here will typically just drift off to infinity, right? Because it's just, let's say, massless particles, and if I produce them in this room, they will drift. And when they reach near infinity, it does make perfect sense, because just particles are flat space. So yes, in that sense, it will make perfect sense. But let's just get the scales of this. Suppose this guy 10m collapsed to 6m over a time of scale m. Okay, so maybe half the speed of light. I'm not producing any other scales. Can you guess what's the wavelength of the particle that we produced? There's only one scale in the problem. So the answer is m. Okay, something of the order of whatever this scale was. We're not worrying about factor of time. Can you guess how many particles will be produced? Well, order 1. There's no number in the scale. There's no scale in the problem. So whenever you take a scale, any length scale, and over the same length and time scale, if you just change the metric by order 1, you produce order 1 particles just because this picture is here. This is the entire theory of field, quantum fields in curved space. There is nothing else to it. This is the cartoon version of it. And so the energy in particles of radius, let's say if this was solar size, so like 3 kilometers, if you produce one particle of wavelength 3 kilometers, it has almost no energy. So even though this is happening all the time out there in the sky, who cares? The interesting thing about the black hole is the metric doesn't stabilize. So let's go back to that picture. This slice was like this. If the metric changes to this new slice is different, the intrinsic metric of slice is different, stretched out, right? Okay, so if the only scale in the problem is m, when you go from here to here, suppose I advance this by order m, okay, everything is order m, so I'm doing like this kind of slicing. I didn't increase this side, I increased this side by m, the metric changes over a scale m, everything is order m, I'll produce of the order of one pair of particles of wavelength order m. Okay, so thus you already know the physics. For a black hole, Hawking quota produced have wavelength order what? There's only one scale, the radius of one particle. Okay, so you produce one particle and going from here. But if the metric had stabilized to this, it would be like here, right? Stars normally collapse and stabilize. Red giant can go down to neutron star, stabilize. It's done, no more particles. But in the black hole, it can never stabilize. You see that keeps changing? It never stabilizes. Every new slice, this part is the same, this part is the same. If you want to join them, you have to have an extra stretch over here. You see the extra stretching? Between every slice and the previous one, you have to make it longer. So the stretching goes on and on. It's like something like a cosmology which keeps expanding and expanding and expanding. Right in this black hole, which looks like something is sitting out there, if you actually slice it, every slice is actually getting longer and longer. You just don't know it because normally you don't look at the inside. But so when you do that, if you have some kind of a wave form here, this is how my slice could be like this, the earlier slice could be this, then it stretches to this, then it stretches to this, then it stretches like that. So if you had a wave like this, if you don't know what happened to that waveform, you can just follow it by the icon method, where the peaks of the waveform just go to the peaks. You can see I've drawn that, peaks go to the peaks. That's the most crude way of seeing what happens to a wave when you stretch the space. Okay, going back to Huygens, this is how you figure out how, to leading order in the icon approximation, how a wave changes. And you see the wave become a completely regular kind of Fourier transform, and now become a very distorted kind of function. And now if you just compute this distortion, which is the calculation Hawking did, you just compute this distortion, you can actually see if this, the harmonic oscillator for this Fourier mode was in the vacuum, the one for this one will not be in the vacuum, and you can calculate how many particles are excited. As we said, you'll get off the order of one pair of particles, and the wavelength will be order m, but that comes out. So we're not going to do the calculation here, but if you actually want to see where the whole calculation is, you're literally just taking a Fourier mode, some wave mode here, every mode corresponds to a particle, but we start with no particle, we put this Fourier mode in the vacuum, but when it gets stretched, it turns out it does have particles, and that's the entire particle creation. Okay, so we're just putting a little bit more flesh on the rough words that we had seen yesterday. We're not going to use any of this, because we're going to come back to our cartoon picture now that we know what's really going on. So at the horizon, this is the horizon, a pair of particles got created. Then you go from there. At the next step, you stretch some more. When the slice stretches more, this particle moves on to this side, this particle moves on to this side, and in the region of stretching, a new pair is created. So that's what is happening. What's happening is you imagine a space-like slice like this room. You leave the right 1/3 apart, the left 1/3 apart, take the middle 1/3 like here, and in one time step, let's say double that. Good. It became longer, right? And you create one pair of particles here. At the next step, leave the right 1/3 apart, left 1/3 apart, take the middle 1/3, stretch it. The particle is outside, goes further out, the one inside goes further in the middle, the stretching, one more pair of particles. And that is the entire process. It keeps repeating. The outer particles are connecting here. You can see the Hawking relation going steadily out. The inner particles are getting left on this slice over here. You can see they are accumulating over here. And the new pairs are being created right at the horizon. So the important thing we have seen from this is, where do the negative energy particles go inside? Where have they gone? It's not like they're joking up any place. They're actually going to be sitting all the way along. How much space is there inside the black hole? The R equal to constant line for all t. How long is that? It's actually infinitely long. There's infinite amount of space in the black hole. So that's actually the reason for why all these magics happen. Once you have a horizon, R and T change roles. So even though the range of R is only 0 to 2m inside, R is not space anymore, R is actually time. There's only finite time before you hit the singularity. Once you fall into a black hole, you'll die in some time. That's all time. How much space is there inside a black hole? Well, the T is now the space, and T in the Schwarzschild metric is mass equal to infinity. So you have a lot of space where you can sit, and that's why the particles are never choking up the region where the pairs are being produced. That region is always the vacuum, and everything is flushed out inside, flushed out outside, and you have really the vacuum at the horizon.
How would you explain infinite space if you're using different coordinates where time is time and distance is distance?
Can you say that again?
If you're using a different set of coordinates where time is always time in and out, distance is always, how would you explain that the black hole is infinite in size inside using different set of, because in this case
So
you're
let's
just
do
using
that.
the nature of the Schwarzschild metric to...
Right, so you could use, for example, the Penrose diagram. If you've seen it, I wasn't drawing it because not everybody would have seen it, but I do know what Penrose diagram would look. Okay, so this is the Penrose diagram of a black hole. What you're saying is that you can actually make space-like slices. The slicing I've drawn here actually looks like this. You go further and further up in time outside, and then come back down inside. And what one is saying is the physical length of this thing is actually divergent. You can put an arbitrary length inside. So it can all be written in the Penrose diagram. They're all space-like slices, but the slices can actually, the diagram, squeezes things near the boundaries. There's a squeeze applied near infinity to bring infinity to a finite distance, but when you actually look at the proper distance, these distances are really going to infinity. That's where it all is.
Sorry, quick question. From the picture that you've drawn, it appears, or maybe it's an illusion, that these slices don't completely cover the full space-time.
You mean because they leave
Because they
this
don't-
region apart?
Yeah.
Good, that's only because I didn't draw it properly.
Yeah.
At any point here, I can take it and curve it down and bring it to R equal to 0. Right? That's my choice. So what happens is, okay, I can start with the slice which is, I should really cover all the particles. Yeah, absolutely right. I'll cover it up to here. And then as I evolve it further and further, okay, at later times I can just make this longer and longer and then come out with this. Indeed, I should take it to R equal to 0. And when I drew this here, this part which comes to me at R equal to 0, this part, I just didn't draw it because I was trying to show you the lengthening of this part. That this is long, that this is longer than this is longer than this is all I'm trying to draw.
But still there will be infinite space inside a black hole with this choice.
Can you say again?
You made a choice. Before you said, look, there's an infinite space inside
Yes.
the black hole, but this statement does depend on your choice.
Of coordinates.
Yeah.
Yes. So what I'm saying is you can actually draw a slice, yes, you can draw a certain slice inside this black hole, which is space-like, stays inside R equals to m, and whose physical 3 volume is divergent. You can't do that in a normal star. If you take this room, doesn't matter what you do to a space-like slice, its 3 volume will be bounded. If I try to make it more go up in time, assuming time is that way, okay, its area actually becomes less because light becomes null. You cannot actually make a sphere in this room whose area is more than pi r square. But inside the black hole, you still have the angular, sphere size, whatever it is. But because this size of that, this direction can be made as long as you like, you can fit an arbitrary large spatial volume. You can choose a slice to fit an arbitrary large spatial volume. It is indeed a choice of coordinates. I didn't have to do that. I can just take this to go like this, and I have a finite spatial volume. But this is more useful to study because it's a good way to understand what is actually happening to the Hawking particles. It is a choice of coordinates. But the fact you can do it is not possible if you don't have a horizon. That's it. Okay, so this is the slide which really shows you a different version of the same Hawking puzzle. If anybody tells you that they found a solution to the Hawking puzzle and they still have a horizon in their picture, which 90% of people do. This is the question you should ask them. What is this question? So you take a black hole, and you know pairs are created, and the black hole mass starts going down. So can you keep feeding the black hole with some particles so that the mass stays back to where it is? You can do that, right? The black hole is evaporating at the same rate. You can imagine throwing in some radiation at the same rate. So the black hole mass remains, if you start with 1 solar mass black hole, you can keep it 1 solar mass. Just gently keep feeding it. What is the picture for that in what we have seen? Well, this is the picture. So the Hawking pairs are coming out, we saw that. This is entangled with this one. This was partner of this pair, this is entangled with this one. This is entangled with this one. Those are the red dots and the green dots. What are the blue dots? The blue dots are the particles that are thrown in. Everything that goes in will end up somewhere on the space-like slice, right? A space-like slice catches every particle projected. So if you like what I've drawn here in this Penrose diagram, for people who like Penrose diagrams, if I throw some matter in, it sits on the slice somewhere, right? These slices, the matter I've thrown in, those are the blue dots. When the Hawking particles are created, they actually correspond to particles going this way on this diagram. This is the outer particle, this is the inner particle, that's the pair of particles, and that will be the green dot and the red dot. Okay, so now I'm just feeding it back in, feeding the stuff back. So now you see the mass inside here comes from these guys and these guys. And now let's ask which of them have positive energy, which have negative energy. So as seen from infinity, this question came up yesterday, so it's good to go back to the context of this slice. When I measure the mass from infinity, it turns out the red particles contribute negative energy and the blue particles contribute positive energy. These were the guys who have negative energy, that's why the negative energy partner of those pairs. The blue guys obviously had to have positive energy because I threw them from inside. At infinity, everything has positive energy, and as you fall into something, energy is conserved. So it can't be that its energy became negative. So the blue guys which are thrown in from outside, their energy is obviously positive. So how do you compute energies in this kind of situation? On any space-like slice in GR, there is a way to compute energy. And now you see, because this R direction, this is your time direction now. And number time is really space. This time, right? This is R direction on here the new time. But this was old t, and the t is actually becomes space. So now you can go both up in the space or down in the space, left and right. So the killing vector del by del t is moving in the del by del t direction. You can go one way or you can go the other way. But if you want to measure the energy as seen from infinity, you need to get the eigenvalue of the t translation of it. But you see, now you can go both ways. Normally when t was time, you can only go with energy is positive, e to the minus iet in quantum mechanics. But now, t the space direction. You can have e to the iet, you can have e to the minus iet, both are allowed. And those are these two guys. One guy made of waves propagating this way, one is made of waves propagating that way, just like momentum in this room can go this way. Okay, but why is this the problem? This is a very serious problem. Because now you see, inside here, I can make this as long as I like, and then bring it down to r equal to 0, just to make it complete. But because I can make it as long as I like before closing it to r equal to 0, I can hold an arbitrary amount of data. Forget entanglement of anything. Just take this metric, forget the pairs, and just draw the short shell metric like this. Just draw this slice. On this slice, put some particle traveling this way, some particle wave traveling this way. Wave that way, wave that way. It's just like a space-like slice, one particle momentum this way, here a particle momentum that way, here a particle this way, then a particle that way. Nicely well separated. Let the separation between them be 3 kilometers. The whole scale of this was 3 kilometers, let's say, the solar radius of the black hole. Okay, gently spaced out particles, nothing, no problem. The total energy of these particles adds up to nothing, so it's still the same black hole. And the amount of data inside here is infinite. I can, for example, carry a spin bit, carrying 1 bit of data on each of these. That means inside r equals 2m, I can store an infinite amount of information with no clash between the different bits. In any model which you make of a field theory where you have only a finite number of states and a finite energy, this is not the solution. Okay, so suppose you have a dual ADS CFT where in a boundary CFT you know that for a given energy budget you can have only a finite number of states, you can never achieve this. So if anybody says that they believe in string theory and in ADS CFT, but they also have a horizon. Horizon is a place where the signature of the metric has changed sign. The first thing you have to go and ask them if the metric has changed sign. And this is a smooth metric to leading order, right? Like this one, the quantum fluctuation, but leading order, there's semi-classical metric, that's the meaning of this picture. You ask him, can I draw this line? He has to say yes. On this, can I have wave going both ways? That's the space direction now. Obviously, the answer has to be yes. So can you hold an arbitrary amount of information here? Well, unless he can give you a reason why not, the amount of entropy inside for a mass m is infinite, and it just cannot fit in this. So this is a crucial version of the, just different version of the Hawking problem, which all comes because you can have negative energies inside, you cancel positive energies, and the moment you have this situation, for example, you can have one in the potential entropy stored on the slice, and that's why it seems that the only way to really get rid of this problem would be to actually not have a horizon at all, which is what I'll come and tell you that we do with the whole first ball thing. Yeah.
In the same way that from outside you don't have access to the infinite volume inside, you also don't have access to the information.
So again, from the outside you can?
So you said that there's an infinite amount of information stored there in
Yes, you can store
an
infinite
infinite volume, but you don't have access to either that volume or the information from outside.
You don't have access. You may not have access, depending on what your process is. I agree you may not have access. Right now the problem is, can you have that state? Because if you can make a state, whether you can access it or not, if you have an exact duality between some gravity and some CFT, for every state I make on a complete space-like slice in gravity, there ought to be a state in the CFT. Now, if you break that link, you may again have a way out of that. Okay, but right now, let me assume that is the link. Every state in a dual description, as Antar will tell you, one is just a collective field description of the other. Suppose just take a very basic attitude that every state on one is a state in the other. As long as that's what you're doing, you have this.
Why is this not a problem for, let's say, some accelerated observer? And there is also there, for him also there is a predictor.
Observer.
There you could also say that since there is a horizon, that there can be infinite amount of information. On the other side, there is...
Yeah, but you have to be careful. Because now we are really worried about how much information we can have for how much energy. Normally when you just do accelerate observers, you draw horizon, it's all kinematic. You're not looking at masses at all. And that is not real energy. Okay, I do have an answer for you, but not short enough to give you now. Okay, and the answer really has to do with the fact you really have to have metrics and energy in order to define which energy you need. If you choose different kinds of time and define energies for different things, they don't have much meaning. There's no bound if you choose some other kind of energy. But here, asymptotically, we just have flat space, and we do have a meaning for energy. With that energy, can there be arbitrary amount of state inside? That is the problem. So this won't actually happen for the accident observer, and I'm happy to say that. Okay, so let's see what do the ADS CFT people tell us about this. So let me talk a little bit about what somebody doing ADS CFT will do. So here's a one-page cartoon of ADS CFT. You guys all know it, so I'm just giving you one cartoon. If this is the antidistant space, you can of course do gravity on the antidistant space, and if you take 2 points in the boundary of antidistant space, you can compute the gravity correlator between them by summing over, let's say, paths of gravitons. So you can do some gravity calculation with a 2-point function where the operators at the function are chosen to lie at the boundary. And ADS CFT tells you you don't have to look at the whole ADS space, just look at the boundary itself. And on the boundary, there's a certain field theory of which those are schematically the diagrams of this Yang-Mills field theory. And if you do the calculation of appropriate operators using this field theory, it will be rather complicated. If gravity is weakly coupled, they're strongly coupled, certain blocks of loops in there for you. So the correlation function would actually be the same. So one guy can be represented by the other guy. And at first that looks like a good thing because the field theory certainly has no problems. It's a very nice field theory. And so you might think the gravity has no problems. And so initially when the ADS CFT thing first came up, a lot of people who were to think about the black hole problem stopped thinking about it because they thought it's gone. And this was actually a mistake. And I'm going to spend the rest of the time today actually explaining to you what the problem of that, what error was made at that time, because it was really very prevalent as a split in the community. Half the people thought about something one way, and half thought about it the other way, and half those people got it right. Okay, so, as you might know, over the last couple of decades, there will be lots of claims and counterclaims about black holes, and now we're just going to start, getting what people have been saying, what part was right and what part was wrong, and why. So, the process will actually give us a very concrete version of the problem. So, after we're done with this, we have a very precise problem which initially we put out in some, we discovered in 75, but it wasn't made all that concrete. Now we really need to make it concrete because at first it seems that there cannot be a problem. We can get a sense of a 3-point function, so when people check this whole thing perpetually for lots of orders. Yeah.
Is there an equivalent problem for ADS black holes as well?
Yes, absolutely. You can do the same thing for ADS. So you take a black hole in ADS, you're going to make sure when the Hawking radiation comes out to the boundary, you will apply some operator and extract the radiation out. You should collect it. If you don't collect it, it bounces right back. So then you can't really entangle the outside with the inside. But people apply operators to put particles into ADS, and you can apply an operator to take the particle out of ADS. Once you do that, it's exactly the same.
In terms of CFT, what are you doing? You are coupling it to something.
Yes, you're coupling it to an external probe.
Reflecting energy
You
out.
can, yeah, if you have a CFD here, like a sample of an Ising model, I apply a probe which creates an excitation. I can apply another probe and pick up the excitation. So exactly the operators we have represented by these purple dots, those can pick particles in and out, and I need to apply this. So otherwise the black hole do the same. And there was a question back.
I was just thinking with that sort of extracting the energy, do you not need some sort of infinite bath on the outside? To
Yes, so I always imagine coupling this outside to really a flat infinity out there. And in fact, that is really the initial context of in which ADS-CFT was discovered. So as you know, ADS-CFT came up from the metric of the near horizon metric of D3 branes. So if I have some D branes in here, they create a metric like this. Far away is flat space, then there's some kind of a throat kind of region, and then here you get an ADS space, and this is a near R equal to 0. Okay, so that's the actual picture of the entire metric. So if you just keep the ADS region, if you just keep this, then the physics of this gravity is dual to a CFT on this bound. If you put it back in the context of where it came from originally, from the metric of branes. But anything which reaches the boundary, you can always go back to the remaining space you have, and a particle that comes here, you can just let it go out. So in fact, all the work we've done with black holes at the beginning, just a little before ADS-CFT, where all the gray body factor and so on were matched for black holes. Okay, the metric was just this, right? You had a near extremal black hole, you had a whole ADS region, and then the radiation used to really come out if you're doing radiation of black holes. I'm just talking about taking it out. If you always reflect it back from here, putting a reflecting boundary current right back in, you can never develop an entanglement with the outside because everything just keeps going right back. It's a technical point, but you have to do that before you can really find the problem.
But if you are like accepting energy out of the CFT by doing this extracting thing, then then the fact that the CFT was unitary, which I thought that naively converted into the fact that whatever process you are doing in radius should also be.
But that is okay. See, you can a completely unitary theory. Like just take the Ising model, it's a unitary theory, right? But I can still add energy by doing something. When you excite a StatMax system, you add energy to it and you take energy out. So the theory of the guy is unitary. It means after I apply the energy, it evolves in a unitary way till I pull it out. So every unitary system does allow probes. And I'm just putting the probes to define the question.
Yeah, one way that to define the problem, but it's also entanglement entropy as well, right? So in this case, meaning, what is the equivalent of saying that, I'm putting in energy, taking out energy, but I'm not, somehow extracting entanglement out of it.
No, you have to worry about entanglement. If you extract something, you will typically take entanglement out also. That's fine. But right now, I was just saying that in the ADS-CFT context, also the gravity problem is still completely perfect. So let me just show that on the next slide. So, if all this thing was working with 2.4K 3-point functions, well, those are low energy processes, but you might as well increase the energy, put something heavy here, so you create a horizon, and you get a black hole. There are ADS short-shell black holes also, so let's just do that. And then if you reach that energy, it should still be something very complicated with CFT. And so at first you might think there can't be any problem, because the CFT is perfectly okay. So you can see there's a problem here, right? There's a horizon. And there's no problem there, so we should just stare at this thing and figure out what's the solution to the problem. So as you can see, the relatives were all very possible. Because then here you will get pair creation here. You can see it's horizon, so I do it this way this time. There's a pair creation. And and then if a particle goes out, and then just to answer the question, if I take this particle out of this area if I want, you can see on the gravity side, I have something which is creating some problem. In particular, for example, I can store, I have an infinite amount of states I can make here because the metric here changes R to T like I showed before. So you have all the same problems. Even if I don't look at the Hawking radiation, that's why I showed the other way of looking at the Hawking problem. Inside here, I can make an arbitrary infinite number of states on the gravity side. But right now, I'm not even extracting anything or anything. On the CFT, for the same energy, I'm only find that much states. You can see the problem here. So then what's the, let me just talk about the entanglement though. So what is the resolution of the puzzle? It looks like the CFT doesn't have a problem and the gravity does. And so what's the answer? So clearly some answer has to be given, and there's an answer initially proposed at the end of a paper on Mandelstam in 2000, and that's what Hawking picked up on in 2004. He said, I don't think there's a problem anymore, I want to withdraw, I surrender my bet. You guys remember hearing all this in the press? Okay, so the big thing, he retracts his claim and so on. And this was all based on the following argument. And the argument was something called the idea of small corrections. So I want to explain to you what his argument was, what the idea was of small corrections. It's a possible solution to the problem which at first looks reasonable. But we'll also find it is not correct. So that's the part which we want to learn for the time we have. So where can I start?
Started at 4.
So I have about 20 minutes. So the idea was like this. At leading order, you create a pair of particles, and this is the kind of thing we were doing yesterday, right? We wrote a particle, electron, positrons, and so on. Okay, so I just have two things. So there could be spins, there could be charges. I just want to write a schematic thing where two things are intact. So let me just write it as 0. I call the particle outside as B, and the particle inside as C. This is just some historical information. So I can have an entangled state, 0, 0, and 1, 1, and I normalized it. This is an entanglement entropy of log 2, and so let me say So if I just keep this as my entanglement, this is the leading order calculation of Hawking. One pair is created, this particle goes in, we saw it was flushed down the black hole, the other particle escapes, the horizon an empty region again, a new pair is created. So how does the entanglement keep going up? At each step of emission, the entanglement grows by the same amount. Now yesterday I had shown you how to do the math of this. Let's just remember the math of this guy. We don't actually need the math, but just to be very concrete about what one is writing, you just write it anyway. If we have a state, total state psi, which is made of adding, let's say, I equals 1 to n pieces, the ith state for the system 1, tensor the ith state of system 2. So if I take system, some state 1 with 1, and then system 2 with 2, like here I have 0 and 0, plus 1 with 1, there are 2 pieces in it, and here there are n pieces in it, the entanglement entropy called as entanglement of the system is log 2. So okay, why is it log 2? If I look at any one guy, and I try to trace over the other, this guy has state 0, if that is 0, that is 1, if that guy is 1, there are 2 pieces to this. This is log 2, so in this case, sorry, it's going to be log n. So because I have only 2 pieces here, the entanglement entropy is log 2. And if I have a tensor product of many systems, like if I have one pair of particles which are entangled, I'll draw the entanglement with a line between them. And I have another pair of particles which are also entangled. And I have a third pair of particles which are also entangled. But they have nothing to do with each other. Then this entanglement contributes log 2. This one also gives log 2. This one also gives log 2. And the total entanglement entropy is 3 times log 2. So as you keep creating more and more particles, your entanglement keeps going up. So after you create n particle pairs, let's say we create capital N particle pairs, what's the total entropy that you have? The entanglement entropy of the outside to the inside is n times log 2. Is that making sense to people? Now we haven't completely defined how to prove this is log 2 and what the math of it is, but that, as I said, is in the notes, and we can certainly go over it if anybody is interested. Or you can just look at the notes. Okay, so if you keep doing this, you have a problem because the entanglement keeps growing, and near the end point of evaporation, we didn't know what to do. But the idea that Mandelstam was proposing and that Hawking picked up on was, look, this is a leading order calculation. And there are always going to be subleading effects on this, right? Everything has subleading effects. And they've got to be small because this is the leading order answer, because you have leading order metric, which is the standard factor metric. So for example, you can have quantum fluctuation. The whole black hole, with a very small probability, can fluctuate into just empty ADS space, which is called thermal ADS. It has just a gas of energy. Same energy, but distributed in a thermal gas of particle, not a black hole. And it can fluctuate back. Is it a likely fluctuation? No, because the black hole has a very large entropy. The gas of particles has almost no entropy compared to that. So the fluctuation is very suppressed by a factor exponential of minus the entropy of the black hole. You know, SBH for the entropy of the black hole. It's an exponentially small suppression. But it's possible. So obviously there are going to be some small corrections which are going to come to this kind of state because of such quantum fluctuations. They are subleading effects. Now, why should you worry about a subleading effect? Well, normally, if the effect is very small, if the total, my problem was because entanglement was n log 2. N for a solar mass black hole is about 10 to the power 77. It's a huge number. So if I just make a exponentially small correction, you might think, why should I worry about this? But what happens is that the number of particles is so large. So when you start looking at possibly correction terms, suppose the number of correction terms was also very large. We'll see them in final as well. If there are a very large number of correction terms, and each one individually small, could it be that the subleading terms actually overwhelm the leading answer? It's possible in principle, right? So because there was no other obvious way, the CFT was saying this thing is fine, the gravity was saying at leading order, the entanglement is growing. The idea was that if you do all the subleading calculations carefully, even though individually every term is actually quite small, by the time you put all these terms together, the large number of terms cancel the smallness of each individual term, and the net effect wipes out the entanglement. If the entanglement of the particles outside with the particles inside, by the time you reach the end of evaporation goes to 0, then is there a problem? No. Whatever is inside can just disappear. The outside guys have a state of their own, and there is. So this was the idea which made Hawking give up this bet, and he was like on the press conference saying, "I've given up my bet." But you can see what the source of the idea was. So suppose you have this is the leading order answer. How do you make it slightly different from there? Well, I can take the orthogonal state to this, which is 0, 0, minus 1, 1. That's the orthogonal state. And I can add it with a small coefficient. You can see this epsilon. The k is just for which levels, which emission step I'm. Epsilon 1 for the first step, epsilon 2 for the next step. I can do that, right? So that means the 0, 0 chance of emitting 0, 0 is 1 plus epsilon k, and chance of getting 1, 1 is 1 minus epsilon k. I made the state slightly different from what Hawking really thought it would be for the normal leading order calculation. Does that make sense? That's a model of a small correction to the leading order state. The leading order state is just an entangled state, 0, 0 plus 1, 1. But if the 0, 0 could be a little bit more than 50%, it could be less than 50%, and that's another possible state. So a small epsilon like that could create a correction. That doesn't look like such a big deal, but let's see what happens when you do 2 steps of emissions. Suppose at the first step you really got this. At the next step, you could make it conditional. If at the first step, suppose you got 0, 0, suppose this was an electron, suppose electron fell inside at the first step, you could say at the second step, the chance of getting another electron might be a little less than 50%. Why? Because of repulsion or something small. And the chance of getting a positron might be a little bit more than 50%. Let me see how I build that in. So at the first step, the BC particles were in 0, 0 state. If that is true, that multiplies this bracket for the second state. You see the square bracket over here? If I got 0, 0 at the first step, I have a little bit more than 1 of 0, 0 at the second step, and a little bit less than 1 of the 1, 1 at the second step. So I said at the second step, if the first step had a 0, 0, as the electron fell in, then I make it a little less likely for the electron to come out at the second step. But if I had a 1, 1 at the second step, the positron fell in, then the 0, 0 is a little bit more likely, and the 1, 1 is a bit less likely. You can see I'm putting in correction terms here, but each step depends on what happened to the previous step. The only thing is all the epsilon have to be small, otherwise my leading order metric makes no sense. So if my metric is still the leading order metric of the black hole, I can still put in these small corrections. You can see how many terms there are. The number of terms you get after n steps is actually 2 to the n. Why? Because every possible state, 0, 1, 0, 0, we don't know all these steps, right? Every state that you get can change a little bit. And there are 2 to the n steps. If you have n emissions, the possible states you could get outside were any order of 0, 1, 0, 0, 1, 1. There are 2 to the n of those steps. Each one could be slightly corrected. So there are 2 to the n correction steps after n terms. See, that's exponential. The suppression of each term e to the minus s black hole, that's like e to the minus n. Okay, so can this small exponential fight the very large number of correction terms and actually kill the entire? So it doesn't look reasonable? At least as a claim. Do you understand the claim? Small changes to each step will remove the whole thing. You can see why it is difficult to prove that though. Because firstly you don't know what the epsilons are, so you're going to make this work for, find some epsilons which will make this work. But let's just at least write down what we are doing. This is the horizon. These are the particles inside. These are the particles outside. And the leading order, this was entangled with this was entangled with this, and there was nothing else. But now you're saying, I'll put a small correlation between this guy and this guy, this guy and this guy. The guys which are not really partners of each other, let's make small corrections to like everybody can talk to everybody, a little bit. Okay? And if we do that, then those corrections, after doing all those little things, I still have to compute the entire entanglement of what is outside with what is inside. And this time the answer should be. Now it's amazing that half the people in the world believe this and half of them don't. It's really a complete split. So let's see who believed and who didn't. So let me just finish the argument. So the argument was, just going back to the kind of picture we drew before, outside the hole you just have normal physics. At the horizon, semi-classical still good approximation with small corrections, right? Not exactly to the minus and small corrections. What happens deep inside, we don't even care. Okay, deep inside near the, okay, we don't care about particles. And those corrections though can pile up and then do something. And so if we take the leading order answers, they're going up and up and up. If you take all these corrections, it may seem to go up, but just like a normal black body, at the end it will finally happen. So that was the idea. And if that happens, there never was a problem. The whole problem for all these 40 years was Hawking the leading order calculation. No one checked us for leading terms, and we were just sitting there like doing nothing for 40 years, and there never was a problem. But why did the relatives ever think about this? I mean, they're not stupid people. And it turned out this is where the whole split came. In fact, the bet had been taken by Hawking and Thorne together with John Preskill, and Preskill said, somehow there'll be no information loss when you finally solve the problem, though I don't know how it will be solved. And these guys had said long back that, we'll pay you if information is not lost. And Hawking in 2004 said, okay, I pay up on my bet based on this argument. Even though he didn't quite know how it would work, but he said, I just sort of think the submarine terms can be big. So he gave a bunch of sports encyclopedias by post to John Preskill, and he surrendered his bet. And his co-signer on the bet, who was, like these guys signed the bet together, Kip Thorne said, I refused to give up. He didn't pay. And he said, look, why should I pay? You haven't shown me how it will happen. And the reason he didn't believe that is for the following reason. So what are we saying about how the entanglement is increasing? At each step, the entanglement goes up by how much? Does anybody remember from what I was writing there? At each step, it goes up by log 2. If you put an epsilon after correction to that, suppose epsilon is 1%, of course very small, you just say 1% for each of them. Suppose it went up by log 2. What Thorne and all the GR people said was, it will go up by 99% of log 2. Does that sound reasonable? And the next step it will again go up by 99% of log 2. And then of course it wouldn't solve anything. Right? The line instead of going here, will go here, and then nothing. While what Hawking was saying was, the corrections are so much that initially it may bend down little, but when all of them are taken into account, ultimately come all the way down. And the relativists thought, okay, you can always put in the epsilon, they also there can be small correction that go here, and the string theorists were all joining up with the Mandelstam and Hawking and saying it's actually done. But the interesting thing is nobody actually made a model of the values of these little epsilon 1, epsilon 2 I was showing you. All you have to do is to make a model, right? Where you can have those epsilons, and such that at the end, when all those epsilons, the entanglement goes to 0. And then of course you have to show that in string theory those corrections are really there. That's the real proof of the pudding of showing. Okay, so this was the problem with the bet. So this is the big debate which lasted for many years. And what I want to show you, in whatever time I have, maybe I won't actually be able to go through the whole proof, but whatever I can cover, that actually you can prove, using the power of something called strong subadditivity in quantum information theory, that actually Thorne was right and Hawking was right. It doesn't matter how many terms you have, the actual entanglement doesn't really go down by more than 1%. If the corrections are 1%, the whole thing will go down by 1%, but cannot go down. The number of particles doesn't actually add up. So how do you actually prove it? So let's make a model, and I'm going to use the power of strong subadditivity and prove this. I think I have 5 minutes and that should work. So outside the black hole, physics is normal. So you can see I've written normal physics here. So once you leave the black hole, means go outside R equals 10 m. That's really up. So I won't change anything. Normal physics. Around the horizon, close to normal physics. Then what makes sense to you? Close to normal physics because it is what Hawking did at leading order, quantum fields on curved space plus small corrections. Don't have to be this small, just some epsilons. It doesn't have to be less than 1. It could be 1% corrections. So close to normal physics, and inside, I don't know. If I start caring about inside, you might say, are you correct or wrong about what happened here? Are you going to go inside? But I don't need any of this. Okay. That was step A. Okay, step A and B. This is our model. Step C. Near the horizon, of course, because space-time is normal, you will get a whole pair being created. So at the leading order, this wave function stretched out to this, and one pair got created. All the things I showed you in the first part. I'm just reproducing all the picture here. Now let's start introducing the notation for what we want to do. So the particles which are outside, as I said, I call them B, and the particles that are inside, I call them C. They are positive energy are B, negative energy are C. So the first particle that came out is called B1. Its partner is C1. It's got deep inside. I shaded this out because I don't care about these guys. But it's there. C1 is there. And then the next particle came out is B2. Its partner is C2. You can see it's there. And then all the way up to Bn. Its partner is Cn. And this is the new pair getting created near the horizon. It's all okay. It's the first picture we saw in the first part of the talk. And so all the guys that have come out at the earlier stages collectively, I'll just denote them by B. Is it okay? The new pair I'll call Bn plus 1 Cn plus 1. All the guys outside I'll just call them connected to Bn. So what after n guys have been emitted, that's called the nth step of emission, and n plus 1 step I'll get a new pair. At the nth step of emission, I have B1 to Bn outside, what I've called B, and I have C1 to Cn inside. And now the notation is like what we talked about before. The word S of a set A. What does that mean? The total space of everything is not entangled with anything. Right? You can have a up, down, minus, down, up. That's a singlet. But if I focus on one guy, That's entangled with the remainder. So the part of the system I focus on is the set A. So it could be like particle 1. If I take a subset A out of a complete set, SA means the entanglement of this space with the remainder. So if I write the total wave function as state 1 of this, times state 2 of this, times state 1 prime of this, plus state 2 of this, times state 2 prime of this, if I have n pieces in that, the S of A is how much? If there are n pieces entangling A with the remainder of the system, if there are n pieces, the entanglement is no. That's all you need. That's the definition of how entangled something is. So for any subset of this system, now there are lots of particles here, right? You can take many subsets. I can look at just one particle and then this is the remainder. I can look at this subset and then this is the remainder. But S of A means this thing entangled with the remainder. That's the notation. So you can now see entanglement entropy at step n. I call it Sn. It's just S of B. Why S of B? This is what is outside. Entanglement of this with the rest is the entanglement entropy after n steps. It's just notation, so there's nothing deep I have said. The reason I'm writing all these symbols down is that the final equation I'm going to use is an inequality, the strong relativity inequality is an inequality among various different subsets that you can take out of a set and what their entropies are. So I'm simply just showing you various sets to show you how you can prove something. But now we come to the interesting part, right? Right now I just had two systems and they were entangled that way. And now I create a new pair here. But my system dividing line is R equals 10m. So if something happens inside this, it hasn't really changed the outside. Well, there's a very basic theorem in quantum mechanics. If I'm one system and you are another system, and we are entangled, state 1 with 1 prime plus 2 with 2 prime. If I don't change, I don't mix with you any further, I don't interact with you, if your state just changes to something else, can my entanglement with you change? No. What you call your state 1 prime could change to some 1 double prime, but there's still two pieces in it, this with that, and second piece with that. So if one system changes internally, but doesn't change interact with the other system, the entanglement between them doesn't change. Just a basic theorem, it's rather obvious. But because that when the pair is greater than this, if this is my system 1 and that's my system 2, at this stage the entanglement still hasn't changed. So entanglement of the outside with the inside is the same amount. It's necessary. I'm just saying very obvious thing because they haven't got a bunch of it. Well, now let's see what the pair is doing. The pair was in this state, 0, 0 plus 1. Okay? You can see the subscript n plus 1 because it's the n plus 1 part. So this was the state of this guy. And if you take the state of this guy, just look at various systems I can make from this. If I take the whole system B and C together, what is the entanglement of that with somebody else? Well, nothing. It was the whole thing was a singlet. 0, 0 plus 1 is like, up down, my down. We just make a singlet out of the vacuum. It doesn't talk to the particles which were earlier inside, doesn't know the particles which were outside. From the vacuum I made a pair, two guys entangled with each other, they don't care about anybody else. So the entanglement of this system with the rest is 0. What's the entanglement of just B with the rest of the system?
You consider any connections, right?
So far no connections. What's the entanglement of just B by itself? Well, B is only entangled with A, it doesn't care about any other particle. B is only entangled with C. And you can just see it. How much is it? No, just repeating everything that you've seen. Well, this was Hawking reading out the thing. Now let's put in the small corrections. If you make a small correction, all these numbers can change, but only by a small amount. This was 0, it can change, but it has to become less than some small epsilon. This was log 2, it can change, but not too much. You can see I put in the small corrections. It can't be more than log 2. If you have 2 bits, you can't go more than log 2. So I put a minus 7. But it can't change by much. These are the epsilons I put. You can make epsilon 1% or whatever number you want. The small corrections are now. Now comes the important thing. How much entanglement entropy do I get at the next step, step n plus 1? So I just stop in a couple.
That's fine.
So at step n plus 1, now the B has gone out. See this particle drifts out? And now it's part of what I call outside. Now that I want the entanglement of all the outside with the inside. Because I want to know what's the entanglement after one more emission. Again, just in terms of notation, what's the entanglement of the outside with the inside now? It's the entanglement of the set B plus Bn plus 1. You see the B plus Bn plus 1? Entanglement of this thing, this set with the rest is what you call the entanglement at step n plus 1. It's also looking completely trivial. Nothing has been said, only notation. And now comes the punchline. So everything is on this slide. If you just take 2 minutes, and you will now see that Thorne was right and who was wrong. Well, this is the great theorem. The strong solidity theorem. It's another non-trivial theorem proved by Lieb and Ruskay long ago, in the 1970s. If you take 4 systems, A, B, C, and D, well, the whole set is made of 4 systems. That's why things will not. If you take the entanglement of the set A plus B, the union of these two, with the remainder is C plus D, let's call that by this symbol. If you take the entanglement of B and C, this system, with the remainder, let's call it S of B plus C, that was our notation. The inequality says that is greater than equal to S of A. A entanglement with the remainder, B, C, and D, that system, plus S of C. C is entanglement with A, B, and D, that's the inequality. Okay, so that's just a standard thing in there, but now let's just go and use it. I have to choose my sets A, B, and C. For set A, I will take all the particles B1 to Bn emitted world. It's my choice, I'm just choosing my sets. My set B will consist of only one particle, the outgoing particle at step n plus 1. My step C is a set of only one particle, the ingoing particle at step n plus 1. Is that okay so far? What I've written here is everything I wrote in the last first slide. This was the notation. I just copied the same thing now, so this should be familiar. Entanglement entropy at step n was S of the set B. It's S of A. You can see how I'm going to use it for a second. Right? Entanglement entropy at step n plus 1. The B had been joined along with Bn plus 1, which also came out, right? So this was the definition of what is S at entanglement at step n plus 1. Entanglement of this pair, the new pair with the rest, it was 0 at leading order. They were just 0, 0 plus 1, 1. But now it could be a little bit more than 0, but not too big, so less than some small number epsilon. Entanglement of C n plus 1, the leading order was just entangled with B fully, and so it was log 2, but now it has to be not much corrected, which is bigger than log 2 minus at most a small quantity. Everything is written on the last 4 slides is actually was fine with this. And now I can actually end with everything. If I take this, I just put, if I look at SA plus B is this one, SB plus C is this one, SA is this, SB is this, and there is my inequality. If you look at what this is what we call S at n plus 1. I'll move this term to the other side. This is greater than Sn plus log 2. There you get it. Let's just read it out in plain English. Entanglement after n plus 1 emissions is equal to entanglement you had after n emissions plus the log 2 which you got for the leading order of Hawking minus at most a small number. So if you're going to go by log 2, but the epsilon is going to say 0.001, so these two things become 0.002 if you add them. You go by log 2 minus 0.002, you keep going up, you can never come. So the reason, what is the whole non-trivial power of this come? The reason it was difficult to see this immediately either way was because anything can entangle with anything, looks so complicated. Right? But the point is the evolution is sequential. So each step when it comes out, what was gone, well that guy is gone. That's the very important thing to put it. If you change that, if something is gone, if you can still keep changing it when it's gone far away, like if you put a wormhole from here all the way to that particle, and even though the particle has gone to a million m, you can twist it, spin and make it from up to down, then this. So that's very important because that's the thing which all the people who are doing wormholes or things like what Papaduma and Rajiv were doing and so on, they want to change the particle after it has gone. And if you don't do that, if you don't have any long range effects which can change things beyond, let's say, r equals 10m or any given number r equals 100m, this is then a complete theorem. This is a rigorous version of what Hawking was doing. It says the emission keeps going up regardless of the small. So as long as you can have non-locality, but only over the scale of m, 2m, 10m. Once the particle beyond some limit, you don't want to touch the particle. That's what happens when you burn a piece of paper. Once the guys go away from the paper, they don't change. As long as that is given to you, the Hawking's problem is now a theorem. You just can't do it. Okay, so I'll end here because now this really sets up the question for us. Because now we have only 2 ways to solve the problem. We can't have information loss instead. So we have only 2 ways to solve the problem. Either the black hole doesn't look like what it does at all. A small correction to the black hole is not happening. That's what it's telling us, right? Either you completely change the metric of the black hole, which people have never been able to do because of a very nice theorem. And what's the theorem called? Black holes have no hair. All black holes have to have that structure. You can have, that's the classical limit or whatever, so small corrections can be there, but black holes have to have the structure. So either you break the low hair theorem and get a completely different metric for the black hole, which is what we do with fast balls. Or you have some completely non-local effect where even after the particle has gone past 10m, 100m, any number that you could think of, you can still change it by some non-local effect. Maybe a wormhole reaches out, does something to it, and then you can fix them. Now there are only 2 categories. And so what I'll start doing in the next talk, I'll show you how the fuzzball thing works out in string theory, and then maybe I'll give you some comments about the non-local things, how you know, what people are conjecturing about how you might do things non-locally, and then we can debate.
Okay, thanks very much for the lecture. Any further points of discussion or questions?
Can I ask, in the argument with entanglement, so in the picture you said, the small corrections, were they saying that the small corrections could be applied to even old pairs that had gone off a long time ago?
Exactly. Can you repeat the question? The package have been emitted. What I was assuming here is that they are not touched anymore. But the pairs which are emitted before, if the pair is coming out now, you can still go and change the spin of that pair.
Okay.
That is what you need to bring there.
Okay.
If the parts which are gone,
Then-
there is no more.
Okay, so let's thanks Samir.